Hi guys, welcome back. This is Chapter 14, Non-Renewable Energy and Electricity. Chapter 15 will talk about renewable energy, and then Chapter 15 will end this unit, so you'll have a lecture exam soon. Here's our learning objectives for this chapter. Again, you can follow along with the notes if you've printed them out. Let's look a little bit about the history of an oil field. How much oil is available on the earth to begin with? What do you think? In theory, the answer to that question is determined by the absolute amount of oil in the Earth's geological strata or layers. But in reality, the answer is a little more complicated because oil deposits exist in different forms and in different places. Some oil deposits are easily available to be tapped or gathered, and others can be exploited only with extreme difficulty. Thus, how much oil is actually available is determined by technologies that are available to extract it, and thus the cost of applying those technologies relative to the price of the resource. There's a river oil field in California's San Joaquin Valley near Bakersfield, where oil was first used by the Yokut Indians. And as technology developed, more oil became extracted from this oil field. And since 1899, about 2 billion plus barrels of oil have been extracted from this field, with only about 475 million barrels remaining. And recovering the remaining oil is really dependent on how good our technology is in getting it out and how high the high oil prices. So here's a look at the Kern River oil field in the San Joaquin Valley, shown there in the light green. This is a look at the Kern River oil field back in 1910. By 1910, there were over 9,000 wells that it had been drilled, but production had already peaked and was beginning to decline. So by now you probably realize that oil is a non-renewable resource. New technologies and increasing demand and prices for oil have provided incentives to maintain production in the Kern River oil field. All right, so energy sources, we'll start filling out some notes, can be primary energy or secondary energy. And primary energy is your first blank. This is energy contained in natural sources such as coal, oil, wind, and sunlight. It can be changed into other forms through a process called energy conversion. And these other forms of energy are classified then as secondary energy, such as electricity or the kinetic energy of an automobile. So we call electricity is when primary energy is converted into another form. And usually that's by using sunlight, wind, coal, or oil to move a turbine or a big blade. And moving that turbine will then generate electricity. End use refers to the final application of energy, such as running an appliance or driving a car. And the energy conversion efficiency is the percentage of primary source energy that is captured in a secondary form of energy. The second law of thermodynamics comes into play, and I promised you I wouldn't use too many physical or chemical terminologies. But that second law of thermodynamics just says that energy is lost during each step of the conversion process. So when we look at energy conversion efficiency, that's the percentage of primary source energy that's captured in secondary form. So it'll never be 100%. Then energy end use efficiency is the product of the efficiencies of all the energy conversions from the primary source to the end use. So for example, 100 units of coal powers a light bulb that produces 1.2 units of light energy. So we would call that 1.2% efficient. Then the big forms of energy are either non-renewable or renewable, and non-renewable energy is derived from sources that exist in limited quantities. So kind of like when you use them, you lose them. There aren't any extra left over. These will include fossil fuels such as oil, coal, and natural gas, and nuclear, which relies on the element uranium. Some renewable sources, these are a little more popular nowadays. These are energy sources that are not depleted when used, or they can be replenished quickly. So, solar is a renewable form of energy. We'll always have sunlight, we'll always have wind, and we'll always have wood from timber and trees. Then, secondary energy just refers to energy transferred from primary energy sources, like we talked about before, such as electricity. The end use efficiency, this is showing the electricity to power a light bulb comes from the potential chemical energy of coal that's burned in a coal-fired power plant. In these energy transformations, like we said before, 100 units of chemical energy is required to produce 1.2 units of visible light energy. So again, this is what we call end use efficiency for this process, and it's 1.2%. End use of an appliance or a car, the rates of primary energy consumption vary by country, and consumption of energy is usually broken into 4 sectors. Transportation is a big one, industry, residential and commercial, and then electricity. The United States, which is less than 5% of world population, accounts for nearly 20% of global energy consumption, which is kind of a crazy statistic. Here's a look at the United States oil consumption gap. So oil consumption in the US has increased by over 3-fold since 1950. So again, think of powering your cars when you're thinking of oil production. US oil consumption. US oil production peaked in 1970 and has started to decline, and it has increased since 2009 for reasons that we discussed or will discuss in a little bit later. The global primary energy sources, you can see here it's broken down into coal, oil, natural gas. Those account for nearly 80% of primary energy. Again, non-renewable sources consumed by humans, and you can see nuclear, fuel, wood, and other modern renewables. Then we get to the economics of energy resources, and this brings us to the next part of our notes. The proved resources of non-renewable energy sources are the quantities of an energy source that could be recovered from known deposits using current technology at current prices. And the reserves to production ratio, we put it as a fraction R over P, is the proved reserves figure for a given fuel divided by a particular year's level of production. And we'll get to energy return on investment in the next slide. So this reserves to production ratio just estimates how long a fuel source will last at a current consumption rate. So again, a really popular ratio that many are wondering about with different energy sources right now. The energy return on investment, abbreviated EROI, is useful energy provided from an energy resource divided by the amount of energy it took to produce it. If it's less than 1, it means more energy is invested than actually produced. And these estimates might vary based on what is included as inputs, such as environmental costs. This is a look at the Powder River Basin of Wyoming and Montana, which is a source of coal for many U.S. electrical power plants that are located hundreds of miles away, and the energy costs associated with this transportation, like the one in these railroad cars, which are transporting the coal, are not included in EROI calculations. So let's talk about coal and what it is. It was formed from plants many years ago. It's deposited in layers of sediment called coal seams, and there's different types of coal: lignite, bituminous, and anthracite. Here's a look at the different types of coal and the energy content per unit weight. It's highest in the coal type anthracite, which is the one at the bottom, and less in the ones at the top. Extraction and processing of coal, it's removed from sediments by underground and surface mining, and then it's cleaned to remove dirt and other impurities. Globally, 67% is used for electricity generation, and 90% of that is in the United States. It's transformed into electricity at a coal-fired power plant. So again, how does coal create electricity? We burn coal in a power plant, and that steam moves a steam turbine. So the steam from the burning of the coal will move this turbine, or a big kind of windmill-like structure, and that turbine then is hooked up to a generator, which creates electricity. World coal reserves are shown for selected regions and countries. Coal is very abundant in North America, Europe, and Asia. Among countries, the US ranks number 1 in coal production, as you can see from this picture. Underground coal mines employ an array of shafts and tunnels. Some of these are used to transport miners and equipment into and out of the mine, and others are used to ventilate the mine and haul the coal out. And you might remember instances in history where people have been trapped in mines if a part of it falls down. So coal mining is very much active today still for electricity purposes. In mountaintop removal coal mining, the upper portion of a mountain is actually removed to expose the coal seam, and the overburden is then deposited in surrounding stream valleys. And again, the coal seam is where the coal is deposited or found. Here's a coal-fired power plant. In a modern coal-fired facility, coal is burned at high temperature to produce pressurized steam, which turns turbines, which are attached to generators. There's scrubbers that remove pollutants from the coal. Steam, not smoke, is being emitted from the cooling towers. And the aerial photo shows a modern coal-fired power plant in Germany. A little more about coal, some of the environmental impacts of coal. Mining destroys habitats in mountaintop coal removal. Mine tailings, which are rock and debris from mining operations, can be acidic. There's usually a lot of exhaust from coal fires, which are releasing numerous toxins, mercury and carbon dioxide into the atmosphere. And fly ash is actually solid material waste that can be reduced from these power plants as well. So this is showing oil and gas reserves formed in porous rocks where there was enough organic matter to produce oil, and then an impermeable rock cap prevented its upward movement. So the natural gas, which is lighter than oil, gets trapped above the coal. These oil reserves can be conventional or unconventional. And if you're on the second page of your notes at the top, we'll answer your blank in number 3. Reservoirs composed of permeable rocks with numerous pores and fractures that hold small drops of oil are conventional. And crude oil and natural gas are found in other unconventional geological settings. Some other types of geological settings where we can find oil reserves are in shale and in tar sands. The existing reserves, half of the known oil reserves exist in the Middle East. About 18% is in Venezuela. That's how Venezuela got in a lot of their financial problems, because their government was actually borrowing money against oil that they were planning to export. 10% is found in Canadian tar sands, and only about 2% is found in the US. Nearly half of global proved reserves of oil are found in the Middle East, as you see there, many in South and Central America, and you can see where the other countries fall for proved oil reserves. Here are natural gas reserves. Again, almost 90% of Europe and Eurasia's natural gas reserves are found in only 2 countries, Russia and Turkmenistan, and the rest are found in the Middle East. Oil extraction and processing then. We're going to get to some blanks here under oil production. Crude oil is pumped from reservoirs and sent to refineries. And if there's enough built-up pressure to push crude oil to the surface, this is called primary oil recovery. And that usually extracts about 20% of the oil in the reserve. After that, secondary oil recovery methods that inject water into the reservoir to increase pressure extract another 10 to 20%. And then oil companies use tertiary oil recovery methods that stimulate the flow of oil by actually injecting carbon dioxide, steam, or hot water into the reservoirs. Some of the rocks are not porous enough to allow sufficient flow. Engineers have developed a technique called hydraulic fracturing or fracking that you'll hear a lot of. And this is just the injection of hot water to produce natural gas from deposits of shale. It involves the use of high pressure liquid to actually fracture the rocks or break them apart. And then sand mixed with these liquids allows oil and gas to flow. So this is a look at what fracking is. It's typically used to extract oil or natural gas from shale deposits several thousand feet beneath the surface. Well shafts are drilled horizontally into the shale deposits and injected with mixtures of liquid and sand to try to extract more oil. Here's mining oil from tar sands in Alberta, Canada. There were large expanses of boreal forest, but they were being cleared out, and then the underlying soils were excavated in order to produce oil from the tar sands. Oil uses. 15 to 16% of oil is used for non-energy products like solvents, fertilizers, pesticides, and plastics. 70% of oil is converted to gasoline. I think we all know that. Gasoline is the big sucker of oil. 7% is converted to aviation fuel, and about 7% is used for heating oil. Natural gas production. Oil companies burn natural gas as waste in the past, and now natural gas is actually captured in pipelines. Fracking is used to harvest natural gas from shale rock deposits, and then it's refined to remove any impurities, and then it's converted to liquefied natural gas, also abbreviated LNG for transport. And the liquefied natural gas is your next blank under number 1 in natural gas production on your notes. Here's a look at shale gas reserves in the U.S. Total reserves are estimated at between 14 to 28 trillion meters squared. And the photo here shows a test well being drilled in Pennsylvania. Natural gas uses. 44% are used for industry, such as producing plastics, fertilizers, synthetic fibers, and firing of furnaces. 25% are direct household energy uses, and 31% and growing are actually for electricity generation. And that's because these natural gas-fired power plants release fewer pollutants and do not produce a fly ash like coal-fired plants. Environmental impacts of natural gas. And this is where we have some more blanks to fill out about 2/3 of the way down on page 2 of your notes. Environmental degradation. Locating and drilling for oil and natural gas presents risks to habitat and wildlife. Transport of oil and spills can cause major damage to wildlife. Emissions such as carbon monoxide, carbon dioxide, hydrocarbons, nitrogen oxides. The combustion of oil-derived fuels account for 31% of all human-caused greenhouse gas emissions. And another impact, whether environmental or otherwise, is just the political turmoil that politicians argue either for or against certain aspects of these policies. These are significant reserves of oil that sit beneath a portion of the U.S. Fish and Wildlife Service Arctic National Wildlife Refuge in Alaska. And environmentalists fear that drilling for oil and the construction of an oil pipeline here would have serious consequences for this very fragile ecosystem. Here's an infamous oil spill from 2010. The explosion of the Deepwater Horizon drilling platform opened an undersea well that spilled 5 million barrels of oil into the Gulf of Mexico, and remnants of this spill continue to regularly wash onto the shores of the Gulf Coast states. This was 10 years ago, but your book was written 3 years ago. So even 7 years after this oil spill was happening, remnants were still being washed onto the coast. Nuclear power. So we'll go to nuclear power. The big one we talk about is uranium, the element uranium, which is your blank at the bottom of the page. So this uses heat generated by fission, which is the splitting of atoms. Do you guys remember what atoms were? If we split atoms apart, that creates a lot of energy. It uses the decay of uranium, and when the nucleus of uranium is split, high energy neutrons are emitted or ejected, as well as other forms of energy. If this reaction is uncontrolled, the result is explosive, like the atomic bomb. But if it's controlled, there's our reserves in many locations, and it can produce 16% of global electricity. So here are where the proved uranium reserves are located. Australia has a lot for some reason, Canada, Kazakhstan, Niger, Namibia, so some Europe countries, some African countries, and then South Africa. In Brazil, some South America too. Uranium extraction and processing, it's extracted by open pit mines. The ore that is extracted is crushed into a fine powder and processed into what they call yellow cake. And the yellow cake is converted to gas and centrifuged or spun down to produce uranium fuel pellets, which are packed into rods. And then these 100 to 300 fuel rods are packed into assemblies, and 3,000 assemblies make up a reactor core. So this is a look at how they get the yellow cake, put it into fuel pellets, into a fuel rod, and then take 3,000 to create a fuel assembly. The heat generated from the controlled fission of uranium is used to heat either water or sodium to extremely high temperatures and pressure. This superheated liquid is then used to generate steam. So again, the end goal is to produce steam that will power or turn turbines, which in turn drive electric generators and create electricity. Environmental impacts, there's benefits and costs that are very disputed. There are large open pit mines, there's thermal discharge, there can be what we call meltdowns, which is when a nuclear plant explodes and releases some of that discharge into the environment, such as the 3 Mile Island nuclear power plant in Pennsylvania, or the Chernobyl nuclear plant that had a meltdown in Ukraine. Radiation can leak. Spent nuclear fuel is referring to fuel that no longer can be used in reactors, and it must be carefully stored and monitored. The good news, though, is that it does not release any greenhouse gases. Here's a look at the 1986 meltdown. Reactor number 3 at the Chernobyl nuclear power plant overheated and exploded, spreading radioactive fallout across much of northern Europe. So this happened in 1986. This is what remains of Reactor 3 at a nuclear power plant in Japan. 6 years after an earthquake and a tsunami, millions of gallons of radioactive water continue to pour into the ocean, and high amounts of radioactive cesium have been detected in fish caught within 100 kilometers of this facility. Here is spent nuclear fuel. It needs to be stored. About 2/3 of nuclear waste is in wet storage, in which spent fuel assemblies are immersed in large pools of water, and the remaining spent fuel is in dry storage, in which fuel assemblies are encased in thick-walled metal casks. So spent nuclear fuel is your blank at the top of page 3. Generating electricity with electric power, the generation, distribution, and use. So this is a look at electric power, where electric current is a flow of electrons through a wire. We measure this current in amperes or amps. That's another blank for you there. The electric power then is measured in kilowatt hours, and the electricity generated in power plants uses turbines to drive electric generators. The charged particles in electric current flow between terminals that differ in electrical potential and are measured in volts. So if you're filling out your notes, number 1 is amperes and number 2 is volts. This is an electric generator. A variety of power sources can be used to spin the central rotor of a dynamo and generate an electrical field, and this one is designed to use steam generated from burning natural gas. Here are alkaline batteries, which use zinc powder and magnesium oxide to generate electrical potential. And batteries are strength of electrical potential diminishes, however, Fuel cells, which is your last blank in your notes, convert chemical energy as fuel into electricity through a reaction with oxygen. Unlike batteries, fuel cells require continuous input of fuel and oxygen to sustain the chemical reaction that generates electricity, and hydrogen is the most common type of fuel cell. Here's a look at a hydrogen fuel cell. The dissociation of H2 into protons and electrons is used to establish an electrical current that provides power to do work. Some environmental impacts of fuel cells. There's an electromagnetic field that's produced by these transmission lines. PCBs can be in the transformers and thus eventually get into the atmosphere when we need to throw these things away. Chemicals from batteries can exist, like lead and heavy metals, so you should always recycle your batteries and never throw them away. And this is PCB contamination wastewater from a General Electric Corporation facility that manufactures electrical transformers actually contaminated the sediments over large stretches of the Hudson River with PCBs. And the company spent about $1.6 billion dredging river sediments. The United States in 2016 declared the cleanup complete, however. And that's the end for this chapter. Thanks for joining in, guys.